Hi there, this is a brand new section. Here we are going to talk about recursion. Firstly, let's identify what recursion is. By definition, it's a way of solving a problem by having a function call itself. In computer science, it's a method of solving a problem where the solution depends on the solution to the smaller instance of same problem. Such problems can generally be solved by iteration as well. The real-life example for recursion can be a Russian nesting doll. Hopefully, you have seen a set of Russian doll. If not, this is the picture how it looks like. At first, you just see a one figure, usually painted wood, that looks like this. If you remove the top half of this doll, you see another slightly smaller Russian doll inside it. You can remove this doll from here and again separate its top and bottom halves. Here again you will see another smaller doll. And if we do it once more, you will see another smaller one. And we can keep going until we find the smallest Russian doll. It is just one piece, so it does not open. As you see, a Russian doll is a sequence of similar dolls inside each other that can be opened, but every time the size gets smaller and smaller. Each time you open a doll, a smaller version of doll will be inside, and you repeat the process until you reach the final doll that cannot be opened. Here, if you think of this big doll as a problem, you can see that the problem gets the smaller instance of the same problem until we solve it. So this technique, making the problem smaller and smaller, is called recursion. There are many properties of recursion, so let's see properties of recursion based on this real-life example. So here, our example of Russian dolls conform with the main properties of recursion. So the first property is performing the same operation multiple times with different input. So we perform this process of opening Russian dolls multiple times, and every time we open it with different size of dolls, which means that the input is different. So first we start from the bigger one, then we continue to the which is smaller, then again we open the smaller one, and this continues like this. So here we opened 10 different sizes of Russian dolls. As you notice that the process of opening all these dolls is always same. That's why in the property of recursion it says the same operation is being performed. So our operation here was opening Russian dolls. Now the second property of recursion is, in every step, we try smaller inputs to make the problem smaller. Similarly, in the case of opening Russian dolls, we try to make the problem smaller. First we open the big doll again, and then the next smaller, and then the next smaller, and so on. Now you might be interested why we are making the problem smaller. Because every time we make the problem smaller, this makes it easier to find the solution at the end, which is the smallest Russian doll at the end that does not contain any other one. This is the solution for this problem. Finally, the last property of recursion is that base condition is needed to stop recursion. Otherwise, infinite loop will occur. Basically, the base condition is the condition after that we will not do any more recursion. We will stop the recursion because we either would have found the answer or the answer does not exist. In the case of Russian dolls, we open the first one, then the second one, then the third one, until we reach the one which is the smallest one. So we have to mention that when we reach the smallest one that cannot be opened, we need to stop here. Now you might be interested, what if we don't provide a base condition? In this case, the system will not know when to stop recursion, and this will lead to infinite loop. So no one wants to get inside an infinite loop, because you will never come out of it. There are even a lot of programming jokes about infinite loop. The one that I like most is, a programmer's wife tells him as he leaves the house, "While you are out, buy some milk." He never returns home and the universe runs out of milk. You see that she hasn't provided base condition here. That's why her husband is gone for forever. So hopefully you understand all properties of recursion. So let's convert this rational example into the code so we can express it in the computer science. So our code for this rational example will be like this. Here we provide base condition as when the door equals 1. So all doors are open. So here I took as a 1 the smallest one, which cannot be open. Otherwise, every time we are calling this same function with one smaller and opening each door. So let's recap what we have learned here. So here we have learned that by definition, recursion is a way of solving problem by having a function to call itself, and we provided real example of Russian dolls, which makes the understanding the logic of recursion easy. So that's all for this lecture. Hopefully you understand the logic behind the recursion. In case you still have problems understanding the recursion, you don't need to worry about this because we will talk about it in a lot more details in the next videos. So see you there. Alright, in this video we will look at why we need recursion. This is a quite difficult topic and many people cannot get the concept straight away. But if you keep practicing, then the concept becomes clear. So you might be interested why we need recursion. There are many reasons for this. First of all, recursive thinking is really important in programming, and it helps you break down big problems into smaller ones. Often, recursive solution can be simpler to read than the iterative one. Recursion is used all the time in nearly every field, in nearly every language. If we compare recursive way of writing code with the iterative way, we can easily see that the recursive code is easy to write. Iterative way of code is basically where we use loops. So you might be interested, if it is easier to write code, can we choose recursion over iteration? The answer is no, because there are situations where iteration performs faster than recursion. So it depends on the situation. So when do we choose recursion? A good hint here is that if you can divide the problem into similar subproblems, then you can use recursion. The important point here is the subproblem must be similar. Otherwise, recursion is not a choice. So how can we know that the subproblem is similar in the nature? So when you hear a problem beginning with the following statements, it's often, but not always, a good candidate for recursion. Design an algorithm to compute AND, write a code to list the AND, implement a code to compute all. Finally, the best way to identify a recursive problem is practice. The more problems you do, it will be recognized recursive problems. The second reason to use recursion is the prominent usage of recursion in data structures like trees and graphs. Trees, the recursion becomes almost mandatory to use. So in the upcoming sections, we will explain tree data structures, and there you will see that without recursion, some operation on trees become almost impossible. But it doesn't mean that you cannot use iteration over there, but in this case, recursion is preferable due to the easier nature to write code. So without learning recursion, the upcoming sections will be extremely difficult to understand. So the third reason is that many big companies ask questions related to recursion during the interview. So to pass these interviews, to get better job, recursion becomes extremely important. Here, at the end of this section, I will explain top questions related to recursion that are asked in the interviews of companies like Apple, Google, Facebook, and Microsoft. So the fourth reason is that recursion is used in many algorithms. As you remember, when we discussed the types of algorithms in one of our previous lectures, we talked about divide and conquer, greedy, and dynamic programming. So the recursion is prominently used in these types of algorithms. So without knowledge of recursions, these topics become very difficult to learn. So now you have an idea of why we need recursion, and hopefully you understand why it's important to us. So see you in the next lecture. Hi there. In the previous section, we discussed what's an algorithm and data structure, and we have learned different types of them. We have also answered the question of why they are important in computer science. So in this section, we will discuss about an important concept, which is Big O. Big O is the language and metric we use to describe efficiency of algorithms. Without understanding Big O notation, it's not possible to develop efficient algorithms. If you don't know when your algorithm gets faster or slower, you will struggle to judge your program performance. This concept basically gives you one way of describing how the time it takes to run your function grows as the size of input grows. Let's look at it in the next example. Imagine a scenario that you have a file on your hard drive and you need to send it to your friend. And we need to send this file as fast as possible. How should you send it? The first thing that comes in our mind is that to send it by email or FTP or some other source of electronic transfer. This is correct answer if the file size is small. It is faster than to take it to your friend physically. What if the file size is really large? Is it possible that it's faster to physically deliver it via plane? Yes, actually it is. 1 terabyte file could take more than 1 day to transfer it electronically. It would be much faster to just fly it across the country. If it is urgent, you might just want to do it. So as you can see, delivery method is changed based on the file size. This means in the first method, the time that is needed for the transfer of file increases as the size of the file increases. On the other hand, in the second method, the time that is needed to transfer a file to a friend does not depend on the size of the file. It does not matter if we carry 1 terabyte file or 1 GB file, the time that is needed for air flight is constant. So in computer science, this is called time complexity. It's a way of showing how the runtime of function increases as the size of input increases. So if we come back our example of transferring a file to a friend, we can easily see that in terms of time complexity, electronic transfer increases linearly with the size of the file, but physical delivery is constant in any size. There are various types of runtimes such as ON, ON squared, or O to the power of n. For instance, to paint an area of W meters wide and H meters high, the runtime could be described as OWH. Some algorithms are faster when the input is small. However, they become slower when the input gets larger. It's very crucial that our programs run faster because they are not executed in supercomputers. If a mobile app users face slow performance from the app, they tend to quit and delete your app. Thus, a proper algorithm must be chosen for our development. Okay, in the last lecture, we have learned what is the analogy behind the big O notation. Now here, we will look at different notations that are used in academics to describe runtimes. But in the industry, people tend to use big O. To understand different notations that are used to measure the performance of algorithm, let's look at real-life example. Okay, let's say we want to buy a brand new car, and obviously we want to know more about the performance of car, which means that we are interested how many liters of petrol it takes to drive 100 miles. Now in case of a car, there is not a standard answer for this question. Even though in any car's manual, it might mention that it takes, for example, 70 liters of petrol for 100 miles, this information is not direct because a car can perform differently based on the condition. This number can be different based on which condition you are driving the car. So if we drive the car in the city traffic, it's obvious that it takes more petrol to reach 100 miles than when we drive it on the highway. And there might be situations in which we drive a car in mixed condition, both traffic and highway. Let's imagine that it takes 20 liters to drive 100 miles in the city traffic and 10 liters on the highway and 15 liters in mixed condition. So here we see that the same car can perform differently based on the condition that we drive it. Similarly, algorithm can perform differently based on the condition that is given. We have three scenarios in case of measuring of any given algorithm. These are the best case, the worst case, and the average case. Let's say for an algorithm it takes 1 minute to execute in the worst case scenario. In the best case scenario, it takes just 5 seconds to execute, and in the average case scenario, it takes 30 or 35 seconds to execute. So with the help of these three notation, we can define the best, the worst, and average cases of algorithm. As an example, let's examine quicksort algorithm. Those who don't know what is quicksort algorithm, you don't need to worry about it because I will provide detailed information in sorting algorithm section about it. But now you just need to know that it's an algorithm that sorts an ordered list based on the selection of random number as a pivot number and swap greater values. Let's look at this example over here to make things very clear. The first operation in this unsorted list targets the entire sequence of numbers. And the number is chosen as a reference for sorting, which is called pivot. It is chosen at random. This time for convenience, let's choose the rightmost number as the pivot. Here, in our case, which is 5. The next thing that we are going to do is to place left marker and the right marker. Left is on the leftmost number and right is on the rightmost number. Quicksort uses these markers to repeatedly perform runs of operations recursively. The left marker moves to the right in each step and compares the number with the pivot number and stops when it reaches a number that is greater or equal to the pivot number. In our case, it stopped in the first case because 6 is greater than 5, which is pivot. Then the right marker starts to move to the left, and this time, when it reaches a number that is less than pivot, in our case it stops at 3, which is less than 5. When both left and right markers have stopped, the markers' numbers are swapped. In our case, 6 swapped with 3. So the operation repeats like this until all elements get sorted. So in the best scenario, all elements are equal and the pass over through the list happens once. So in this case, time complexity will be On, because we are passing through all elements only once. And so if we have n elements in the list, our time complexity will be On. In the worst case, if we are unlucky, the pivot is repeatedly biggest element in the array, so the time complexity will be On squared. And in the average case, sometimes the pivot number will be very high and sometimes will be very low, but it will not happen over and over again. So in this case, time complexity will be On log n. Okay, hopefully this example makes it clear and you have understood all three cases. Now to express different scenarios of algorithm, there are three different big O notations. The first one is big O. It's a complexity that is going to be less or equal to the worst case. For example, if we want to sort 1000 numbers, big O measures the maximum time we need for this sorting. Let's say we need maximum 10 seconds to execute this algorithm. This means that the execution will never exceed 10 seconds. It can be 8 or 9 seconds, but it will never be more than 10 seconds in case of big O notation. Then the next notation is big omega. It's a complexity that is going to be at least more than the best case. It is different from the big O notation. Here, we measure the minimum time that we need to execute an algorithm. There might be cases that we want to know minimum time of algorithm execution, which means that if the best scenario for the execution of an algorithm is 2 seconds, in terms of big omega, it will never be less than 2 seconds. For example, if we want to sort 100 numbers and we know that in the best case it takes 2 seconds, it will never be less than 2 seconds. Sometimes this information is useful for us. Now, in terms of big theta, it's a complexity that is within the bounds of worst and best cases. This means that if we have an algorithm with maximum execution time 10 seconds and minimum execution time 12 seconds, in terms of big theta, the average time will be 6 seconds for execution. Okay, let's look at real example for these three notation. Let's imagine that we have an array of 1 million elements over here, and our goal is to find a given number within this array. If we want to search a number which is located at the end of this array, in our case which is 9, we basically check each element one by one until we find the element that we are looking for. In this case, we will visit all elements of this array. Let's say the time that we need to visit each element is 1 millisecond, so the time that we need to visit all of elements will be n multiplied with 1, where n of elements in the array. Okay, how can we represent this searching process in terms of notations? So in terms of big O notation, it will be On. This means that the maximum time that we need to find any given number within this array is n. It will not be more than that. As shown here, to find the last number in the array, which is 9, it takes n multiplied with 1. So it will not be greater than On. In terms of big omega, it will be omega 1. This means that the minimum time that is required for finding any given element is 1. It will not be less than 1 to find any given number within this array. In our case, it will never take less than 1 to find first element in this array. In terms of big theta, it will be theta n divided by 2. This is the average time that is needed to find any given number. This is because for finding different numbers, we need various units of time. So we need to take average of these numbers. We need to know all these three notations for academic purposes. But when it comes to the interviews, we only need big O notation. And that's all for this video, and hopefully you have understood three different types of big O notations.